It's a pleasure to be here. It's my first visit to Purdue. I've always wanted to visit, and it's a lovely day, so I'm excited to be here. So I want to tell you a little bit about the work that has been going on in my group for a few years, but the focus will be on some of the latest work that I'm kind of excited about. I also attached a paper to my abstract. It's forthcoming in Econometrica in the month of March, where you can see more of the technical details. This is mostly the work of my former students. I just take credit for them. Puya was my PhD student and is now, he liked doing homework so much that he's a second PhD student in economics. He's about to finish his second PhD. Ali Reza is an associate professor at the econ group in the Kellogg School at Northwestern, and Amin is a postdoc in our institute. So, as you heard earlier, my research has been the past few years on multi-agent coordination and control. Mostly up to 2008, 2009, my research was mostly on this side. I was interested in studying collective behavior in networked systems and sensor networks, robotic networks. Was sort of interested in problems ranging from motion coordination, flocking, was trying to learn more from how animals aggregate in social groups and what we can learn about them for modeling and designing control systems for coordination of robots, consensus processes, coverage in mobile sensor networks, synchronization, and so forth. And around 2008, 2009, I got interested in understanding collective behavior in social systems, mostly from the influence of my PhD students who thought that this would be an interesting area to explore. So I became a student of social sciences, and tried to sort of understand how people view social processes, how they model them, and basically how we can try to reason and understand decision-making in groups of people. And so I've been working on collective action and collective coordination and social learning, which is the main topic of this talk, which is the problem of how groups aggregate information and combine their observations and opinions and actions of others. I've also worked on contagion, cascades, and some interest in the problem of systemic risk in network systems, which is basically this idea of how networks can get disrupted by idiosyncratic shocks that might affect small parts of the network, but somehow have systemic aggregate effects. Examples of that are things like the financial crisis and the power outages and so forth, where certain failures that are seemingly localized somehow have systemic global effects. The kind of tools I use in my research are sort of a combination of decision theory, dynamical systems and control, network science, and I've been working in a variety of application domains. The work that I did in the first 7-8 years, 2002 to 2009, was mostly around these topics. Basically, how do we get multiple dynamical entities that are interconnected in some networked setting? Now, this network is oftentimes constructed from proximity by making simple mathematical abstractions. And then the idea is if these nodes or agents have limited actuation or sensing authority, how can you get them to do interesting things in a global way? And how does these local behavior of information exchange and local actions diffuse in a network into an interesting global behavior? That might relate to problems such as control of vehicle platoons, where the question of interest is how do you make sure that disturbances don't propagate? Basically, and if you want these automated vehicles to move together in a group, let's say a line, and then you want to stabilize vehicle distances, regardless of disturbances that might come in, how do you make sure that disturbances don't propagate backwards? Other problems include, coverage control. You have a bunch of aerial vehicles that have a sensing footprint. and you want them to coordinate so as to sort of cover or surveil a domain. Or if you want to do cooperative path planning for a collection of robots that have different characteristics, or you want to monitor an infrastructure, or you want to allocate a resource like bandwidth in a complicated network, or want to do distributed sensing, estimation, or inference in sensor networks. So there's been I've been working in this area for some time. There's a large community of people across multiple disciplines who've been also contributing to this domain. And I should have listened and changed the batteries, but I didn't. That's OK. So since 2009, 2010, my interest, as I said, has shifted to problems that have, on the surface, have similar characteristics. Again, you have a bunch of agents that are interconnected in a network. These could be financial systems or banks, or it could be a collection of people in a social network, or could be economies. And the idea is that something is either spreading or diffusing, and you want to either maximize the spread or you want to stop the spread. So in the case of epidemics, you want to basically use limited resources to stop the spread. And in the case of viral marketing, you want to maximize the spread. You have an idea or a product that you want to spread throughout the network. And then there are social and economic settings where decision-making is far more complicated. Individuals have, there's much more endogeneity. We know far less about how actually people behave. And any theory that we create are sort of very, very abstract cartoons of what the reality might look like, just to sort of get some basic insights. But the key idea here is that you can't just model people as automatons that follow certain prescribed rules. So there might be strategic behavior and so forth. So in terms of understanding how certain events and social cascades like the Arab Spring start, how sentiments of the investors result in bubbles and things like that. And so you can ask a lot of questions where, how to stop a spread, maximize or minimize it, or more importantly, what is the effect of the underlying structure of the interconnection between these agents and the question that you're asking. So this has given rise to this area of network economics, which has been growing in the past decade or so. The question that I want to talk about and spend most of my time today is about problem of social learning and distributed inference, depending on what community you come from. It has different names. And this is a problem that actually ties both sides of this engineering or technological and social systems. It's a very natural question that comes up across multiple domains. And it's, roughly speaking, the following. If you have a collection of people or sensors that are spatially distributed, that make some, and these have different characteristics. They make this, if they're sensors, they make disparate measurements. They have different sensor characteristics, different noise models. They might be even measuring different things. One way to sort of make sense of all these measurements is to have a centralized aggregator where all these nodes communicate their information to some centralized brain, and that brain does all the processing. Another way, which more and more we're interested in, is to see how we can actually make sense of localized processing and sort of aggregate this information locally in the system. So if you make these disparate measurements, how should these measurements be fused together? Given that individuals might not share the measurements, but they might share what they think those measurements mean. In the social setting, you have people who might interact in a social network, whether online or offline. And they have their own private observations and experiences. And then they also exchange their beliefs with people in their social peers without necessarily sharing their observations. So the question is, given a structure of a social network, what happens when people exchange this information? How would they actually fuse their private experiences and observations and beliefs and opinions of their neighbors? So that's the central question, how to combine private observations and peer opinions, given that we know there's a long line of empirical evidence that individuals are affected by what others in their social clique do or think. So this is whether you want to decide what political candidate to vote for, or decide what theater to go to, or what restaurant to go to based on the observations and opinions of others, or other things. And so this is, of course, not a question that we've come up with. It's been around for many, many years in one way or the other. In fact, it forms the basis of decision theory going back to at least 50s or even way before then. And so it's a natural question to ask. It comes up across multiple domains from various disciplines in engineering, whether it's control, information theory, signal processing, communications, or in statistics, where you want to sort of understand how probabilistic opinions or information is combined, to decision theory and economics and operations research. So this has been studied across multiple domains. And this is sort of a cartoon characterization, but you can divide this work into roughly two camps. So one camp models that follows the axiomatic work that Savage developed that forms the modern microeconomics theory, really, is basically based on a Bayesian formalism. The belief that individuals or idealized agents are rational utility maximizing agents that make a decision that, given the uncertainty, maximizes their expected utility given all the information that they have. This has been, of course, the basis of decision theory and microeconomics. Then you can ask a lot of questions from Aumann's seminal work in 70s on how rational individuals can agree when there's two of them, to the work of Vivek Borkar and Praveen Varaya, to in economics. In 2003, there was this work of Galen Kariv that tried to bring this to a network setting. There's been a lot of work in economics on this literature, but that's mostly focused on rational, or as we call it, Bayesian decision making. And in this talk, I'll equate the two. Under certain settings, the two are essentially equivalent. Then there's this other camp that basically believes, well, individuals might not be fully rational. They don't have the cognitive ability to do rational processing of all the information. As we will see, especially in the network setting, the amount of processing that you have to do is quite a lot. And so there has been this proposing of various heuristics models of how people might myopically update their opinions or views and observations. So there's also that camp. And these two things have somewhat developed separately, going back to how people might come up with heuristics for combining opinions. This has a long history. This paper that I put up there is by Maurice de Groot from early 70s, which suggests one way of combining probabilistic opinions, if you think of opinions on a certain topic as a probability vector on how much you like each option. Then one way is to have individuals in this network repeatedly average their opinions to reach some form of a consensus. There are other ways of doing this. Okay, so you might say, why do I average? Maybe I form the geometric mean. Maybe I do some other function. People have been studying this, in fact, since the early work of Savage. There's a long history of why averaging may or may not be the right thing to do, and what are the properties of it. And this spans across multiple disciplines, as I said, from economics to statistics, even philosophy and political science. So this is sort of the heuristic side. The rational, or as we call Bayesian approach, is based on basically application of the Bayes rule, which we all learn in undergraduate probability. That if you have some uncertainty about which state of the world, let's call it theta, might be true. You have a probabilistic model, let's say in this case L, or on the right side I call it P. This is the model that tells you what is the likelihood or the probability of observing this observation given whichever state is the state of the world. Then the Bayes rule allows you to flip these probabilities and tell you what is the probability of this state being true given that you observed the signal S. So this is something we learn in undergraduate probability. It's a log linear form with sort of the normalizer in the denominator that tells you the probability, the total probability of observing the signal S. So if we want to think of it in a social setting, you have a likelihood model, which serves as that probability of S given theta. Throughout, I'm going to denote that with L. And I denotes a generic agent. And theta is whatever the state of the world is. So imagine that we have multiple states. We want to decide, do we want option A or option B? Let's say it's a discrete choice. It doesn't have to be. And then you have some prior belief, which could be this probability that you have on theta. This is your belief at time 0. You get a stream of observations. And then you update your belief. You deform this probability distribution according to that Bayes rule up there. And you can do it recursively if you get more and more updates. So this is something that we've known how to do since the work of Doob in 1930s or 40s. We can show under what conditions this probabilistic update converges. This is probabilistic, or this dynamics is random. Why? Because this observation is random. You have this probabilistic model L, which is the likelihood of observing this observation, assuming that state theta is the true state. So I call this shorthand so that I don't have to write it all the time. Call this BU, or Bayesian update. This Bayesian update is a function of some prior and some observation. Right? The observation will tell you how to deform the prior to compute what we call a posterior. And if you have IID observations that keep coming on, then you keep updating and updating. For example, if you're trying to decide what the bias of a coin is, whether it's 50-50 or 60-40, you keep observing, making coin flips, and depending on how many heads or tails you get, you adjust it according to this rule. And so this is something that we can, as a senior undergraduate course or a first-year graduate course, we analyze this as, because these beliefs form a martingale. We know under what conditions things converge. The beliefs converge exponentially fast to the truth if the observations are IID, meaning that this probability gets concentrated on the true state eventually if you have rich enough observations. So all of my talk is essentially based on how does one do this in a network setting. So there's the prior, there's the likelihood or the probabilistic model, there's the observation, and this is the probability of the observation. So that's the question that we want to ask. Now, it turns out, and people have empirically shown this, that doing this in a network setting is hard. If you experiment with people, every experiment that exists, it's hard to do experiments in these settings in networks for a variety of reasons. But whatever exists, the evidence points out that people are far away from this fully Bayesian formalism. And the reason for that is that if all you hear from others is their belief on what they think is true, it's not always easy to invert what was the observation that led them to that belief, even if you knew what their prior was. So even if I know what they thought before they made any observation, okay, trying to solve this inverse problem of what was the belief that led them to that observation in a network setting is not easy. Because in the end, what you're trying to do in this decentralized inference problem is to emulate what the centralized inference would be. The centralized inference would be applying the Bayes rule that I showed you earlier to all the observations of all the agents. So if you had all the signals, all the measurements, you could send that to that centralized brain, and that brain can do the inference for you. The problem here is that each node's belief or probabilistic opinion is updated not only based on their observation, but based on the belief of their neighbors, which is updated by their observation and the beliefs of their neighbors, right? So given that you only see what's around you, this entanglement of what was the observation that led to the belief that is being reported to me is not an easy task. So this is why this might be a hard problem. So, but what does this mean when we say hard? So far, evidence in the literature says that this is when you try to do experiments with more than 2 people, you can't, things break apart. So that you can't actually stay in this full rational setting. So without going into too much trouble, very recently with my colleague Elhanan Mosel and my former student Amin Rahimian, we've formally shown that actually this as a decision problem is a computationally hard problem. So not only it is cognitively difficult for people to do, in the worst case, meaning for the worst realization of signals and networks, you can encode well-known computationally hard problems to this inference problem. So what is this inference problem? It's just one stage or one step of this inference. So given a network, given observations, I want to compute their posterior in the same way that a centralized agent with access to all the observations would do. And so we show that in the worst case, if you let the degree of nodes in the network grow with the dimension of the network, then you can encode some well-known hard problems into this without going into. So there are 2 well-known hard problems. One is called subset sum, the other exact cover. You might have seen these before. If not, it doesn't really matter for us. These are basically well-known problems that you can encode them as an integer program. Or if you solve these problems, then you can solve a lot of other hard problems. Okay, so what we've shown is that this problem is also computationally hard. OK, so the full Bayesian setup is hard in the worst case. And I have to emphasize, this doesn't mean that you can't really do this. Right? There are plenty of hard problems that we actually solve all the time. This is sort of perhaps a very rough notion. It's a worst case notion. That is perhaps only of theoretical interest. In this particular case, though, we know that for people at least, even going from 2 nodes to 3 nodes is a huge hassle. OK, so let's go back to this de Groot model. Or yes?
So missing a piece of what you're saying. So how exactly are neighboring beliefs? How do they enter your Bayesian update?
Oh, OK. So okay, good question. So what you have to do is you would have to basically keep a list of what are the possible observations that they could have had. And every time they report a belief, you refute the ones that are inconsistent with the observations that you see.
Okay, then you
Yes. Yeah. And we show that you can actually encode this hard problem in this. Of course, the trick here is that we need the degree of the node to grow linearly with n for this encoding to work. Either the degree of the node has to grow, or the diversity of the distribution of the observations. How many bins are there in the distribution? We can do binary 0, 1 if we let the degree grow. If we keep the degree bounded, we need the distribution to, as the diversity of signals needs to grow.
So this should, in some sense, translate lights over your neighborhood.
Kind of, yes. Yeah. OK, so now given that this is a hard problem, let's go to this idea of consensus, which is something I've worked on early in my career, mostly based on trying to come up with models of motion coordination with robotic systems. But if you do a bunch of transportations, essentially it becomes something like this, which is the fact that, suppose we all want to decide whether we should grant tenure to candidate A. You know, it's a faculty meeting, a bunch of people sitting around in a room. They want to decide, okay, so you give opinions from 0 to 10, right? Different people have different opinions. And then you have, let's say it's a large group, so you have a localized structure. Repeatedly, you observe your opinion with that of your neighbors. So again, from basic analysis of, you know, non-negative matrix theory or Markov chains, we know that if the graph on which this happens is connected, and if you include your opinion when you're doing this update, meaning that there's an irreducible and aperiodic network, then this update is given by a non-negative stochastic matrix, which means the sum of components on each row add up to 1. Why is it stochastic? Because you put some weight on the opinion of A, you put some weight on opinion of B among your neighbors. And then in the end, you converge to some weighted average of the initial opinions. And so you could think of that as the consensus opinion. Okay, so if your goal was to reach consensus, then this is a nice algorithm that works well. Because it's very localized, you don't need, in fact, you can do this asynchronously. It's also robust to delays. You can add nonlinearities. You can add noise. There's tons of things you could do. You can even allow the networks to change. All sorts of things you could do with this and would still work fairly well. The problem with this, of course, is that what kind of a weighted average do you get? Well, all the information is buried in this vector, which we call the top left eigenvector, or the eigenvector centrality, or the Perron vector of this non-negative matrix. So the problem is that these opinions are weighed by nodes' importance in the network, by how connected they are, how central they are, not by how informative their observation is. It also has a problem that the update suffers from what you might call redundancy neglect, right? You might be paying attention to something that you spread across the network yourself that has gone around and has come back to you. So if another way to see this is if 3 people tell you something similar, because you're averaging, you give it 3 times the weight. But you don't really look to see, well, maybe there was one person 2 hops away that gave these 3 people the same exact information. So you are overvaluing information just based on where people are in this network. And it also doesn't allow for arrival of new information, right? This is, you know, I have one observation at time 0, it's initial opinions or observations, and then you keep doing this. OK, so a few years ago, we had a paper where we said, OK, let's try to inject some more rationality into this. We can't do the full Bayesian thing. Let's do a half Bayesian thing. So we said there's too much of a cognitive burden. And the half Bayesian thing is, well, act Bayesian only with respect to your private observation, not with respect to the belief of your neighbors. So first pretend that you have no neighbors. You get an observation. You had a prior, compute your posterior. And then average that posterior with the prior of your neighbors. Or if you like, average the log. We showed that actually both of these schemes work. That in connected networks, if observations are rich enough, you eventually converge to the true state. You not only reach consensus, but everybody's beliefs will be consistent with a belief concentrated on the true state. So everybody will discover the truth if the truth is discoverable, meaning that if the observations are rich enough so that a centralized agent with access to those observations could find the truth. And it would be exponential, and you converge, you know, to the true state. But then we started thinking, well, what's so special about averaging? Why does averaging work? Why does averaging of the log work? OK, I don't know how people actually do this. So I can't really say I know what the functional form is. But what are the main guiding principles? How can we come up with a foundation for how people might be doing this? And how is this different from the Bayesian updating in a network setting to begin with? I can't even write that Bayesian update in a network setting down. It's so complicated that if you try to write it down even for 3, for like a triangle, you know, the equations get out of hand. So how do I do this in a general network setting. So instead of focusing on particular functional forms, from now on, we're going to try to forms actually make sense. What should these updates look like? So it's motivated based on the same idea, but we now want to lift this to a slightly more general setting. So there's a bit of a notation here. I'll try to go through it slowly and explain what's going on. So what was the guiding principle of this heuristic update that we came up with here? It basically said first do the Bayesian update on your private signal, then aggregate that with your neighbors. And you keep doing that over and over again. If you keep doing that infinitely many times, you could also think of this as the other way around, that you first average your opinions with your neighbors, then you think of that as an interim belief, and then you run the Bayesian update on this interim belief with the observation. These two are equivalent because you're doing it multiple times. It doesn't matter which one comes first. You're supposedly doing this infinitely many times. We live in asymptopia, right? This is, this asymptotic land, nothing matters. Okay? So now I'm saying instead of averaging of the function or averaging of the logs, let me write the most general update that I can even think of that encompasses possibly everything, including potentially the Bayesian update that I can't write down. So for that, I designed something or introduced something called a social learning rule, this function FIT, and I'm going to allow it to even be time varying so that at different times I could use different functions. So this social learning rule, what does it do? It takes my beliefs, my neighbor's beliefs, for all the entire history of the past, mixes them up in some way, produces some interim belief, and then I run a Bayes rule as if I'm one agent on this mixed up interim belief. So this belief is some fusion of my own belief at the previous time, my neighbor's belief at the previous time, but not just the previous time, the entire history. Why the entire history? Because the Bayesian belief will depend on the entire history. In fact, the reason the previous update, heuristic updates, have this redundancy neglect problem is that they do not include history. You take the last thing that people tell you, like some other people I know, that their opinion changes based on who they talked to last. One day policy A is good because I talked to this guy. One day policy B is good because I talked to another guy. So I suffer from basically recalling the past or neglecting the history. So the full update will have to keep track of the history. So you have to drag the history with you at every point in time. That's why we introduced this notation where T is a superscript to denote that we're keeping everything from time 0 up to time t minus 1. And I'm keeping everything based on my own belief and my neighbor's belief for all this time. OK? And now I run some function on that, compute an interim belief, and then I run a single agent Bayes rule on that. OK? So this is now our lifted, far more general problem. And we say, it's because I don't know exactly what rule people follow, let me encompass into a large family that potentially includes everything, including the rational update. OK? And then see what properties this function should satisfy. So I'm going to assume a bunch of axioms on this function. The first axiom is called label neutrality, or we're going to call it LN for short. Label neutrality means that if I permute the index of agents and then I aggregate their information, I should get the same answer if I aggregate them first and then permute after. That I should not care about the indexing of the label. OK? The second axiom is a little bit more complicated. It's what we call independence of irrelevant alternatives. So what does this mean? This means that if I'm updating my belief on a particular state, whether choice, my belief on choice A, then I really care about what my neighbors think about choice A. Right? Their opinions about choice B is irrelevant to me. In other words, if I care, and I can do this for any subset of choices, if I care for only a subset of states, if I condition my neighbor's beliefs on those subsets and then aggregate them, I should get the same answer as if I aggregate them first and then condition later. And single agent Bayesian satisfies this. The Bayesian in a full network also satisfies this. And Bayesian in some networks satisfies this as well. Not all networks. There are pathological cases where the Bayesian update doesn't satisfy. So these two are still satisfied by Bayesian as well. The third one is, and I don't want you to parse through that alphabet soup. I'll just explain it in words. It's some form of monotonicity. It basically says if I have two belief profiles that were exactly the same, so mu and nu are two belief profiles on the entirety of the states. They were the same for all neighbors except for one. The value was lower on some state theta hat, and now it's become higher for some state theta. I should take that as a signal that the aggregation should also increase the value on state theta. So this function has to be monotone with respect to this history. Okay? It doesn't have to be monotone in exactly the previous immediate belief, but it has to be monotone in this history. So this is what we call monotonicity. That's also satisfied by the Bayesians. Our main departure from the Bayesian rationality, which at least we think it's consistent with how people might be making decisions based on these heuristic rules, is that I ignore the dependence on history. In other words, when I listen to people, I don't keep track of, like 5 days ago, what was their belief on this topic. I assume that what they're telling me is a sufficient summary of everything they know, which is not true, but that's the cognitive limitation that I have, that I ignore this dependence on history. So my aggregation function, this sup t really here, only depends on my own and my neighbor's belief on the previous time step, not the entire history. Or I assume that these beliefs are Markovian, even though they're not. Okay? So here's the interesting thing. Even though this log updating of the belief was a heuristic, a hack that we had tried, it turns out that just from these axioms, you can prove the only functional form that satisfies this update is a log linear model. That if you look at belief ratios between two states, the resulting has to be a time-varying linear combination of log ratios of beliefs. Okay? And there has to be some constants that are non-negative. The non-negativity comes from monotonicity. Basically, the log structure comes from this independence or this commuting with the conditioning operator that we assume. So notice that the linear averaging did not pop out of these axioms, which means the linear model of averaging should violate something. Either our proofs are wrong, which I don't think so, or it should violate one of these assumptions. So if I look at these axioms, this means that this is exactly the functional form of my beliefs, which is exactly the ratio of beliefs of the heuristic that I showed you earlier. So we can rederive this heuristic based on these axioms, which basically say that you look at the log likelihood ratios, and then you add to that a linear function of log belief ratios for some constants aij. OK, so now the question is, what happens to this update? When does this update converge? So in order to tell you when this update converges, well, I have to know something about these signals that are coming. Let's assume that the signals are IID to make life easy. Then I need the network to be connected. That makes kind of sense. Otherwise, information doesn't diffuse between different nodes. But what other conditions do I need? Well, I have these weights. How should these weights be adjusted? And here's where we found an interesting connection in terms of when this works and some literature in social psychology on a topic called group polarization. So group polarization is sort of a classical topic in social psychology on tendency of like-minded people to make decisions in groups that are more extreme than the opinions that they had before they met each other. So they're all like-minded, but they sit with each other, and then they become suddenly more extreme. That the center of gravity of groups' opinion shifts, to the more extreme side. There are various prevailing explanations for this. This is sort of very qualitative, somewhat empirical, but mostly discussions in this literature. There's one called social comparison theory, another one called information influence. Roughly speaking, one basically says people try to distinguish themselves from others. So the way to do it is they make themselves more extreme. The other is that they try to elicit basically more response by being more extreme to see how people react. And so no one knows actually which one of these make more sense. Not even sure that the empirical work is rigorous enough to give us any judgment on this. But here are two cartoons of this. So suppose you have a group of people who want to make a decision on a policy. Okay, smoking is bad. They get together. Someone says smoking kills. In the end, the aggregate decision of the group is, let's say, smoking should be banned. And that's sort of an example of where, the things shifted further. Or another example is, you take two groups of people on some topic. Some of them have high prejudice on this topic. Some of them have low prejudice. Then you get them to discuss, and then you see that the opinion gets shifted. And this is sort of consistent across the board. That after discussion, you see this shift. So we can sort of mathematically characterize what this shift means in our network. So if we think of these weights in our log linear model, we call the social learning rule, which depends on these weights, group polarizing when the spectral radius of this non-negative matrix is strictly greater than 1. That means that, so spectral radius is the largest eigenvalue in modulus for a non-negative irreducible matrix. It is actually an eigenvalue, so you can drop the absolute value. It's the top eigenvalue of this A matrix. It's basically where the corresponding eigenvector we talked about represented the centrality. So this basically means there's a direction along which opinions get amplified. And we say, so social learning rule is group depolarizing if this number is less than 1. This means that opinions get attenuated. Okay. And then we say it's non-polarizing if the spectral radius is exactly equal to 1. Okay. Turns out, for learning to happen in this model, you need opinions to be non-polarizing. It's necessary for them to be non-polarizing. And this kind of makes sense. If you want all the opinions eventually to get concentrated on the truth, assuming there's enough information in the observations, you need the beliefs to be non-polarizing. Why is that? Because you don't want to amplify misinformation over time, and then you don't want to attenuate good information. You need to let the information from the observations diffuse in the network long enough so that the law of large numbers does its work eventually. And then you get that all the information buried in the signals gets aggregated correctly. Okay, so it's so because we're averaging the logs, no. So if you want beliefs to go to 0, you want the logs to go to negative infinity, right? Right. So we're averaging the logs here. But what happens is that if beliefs are non-polarizing, so what's the converse, basically? That's your question. Okay, so you could have, in one case, you could have convergence to the wrong belief with positive probability, meaning infinitely often you could converge to the wrong belief. In the other case, where the opinions are depolarizing, you could remain uncertain forever. Basically, you will never figure out. Everyone remains uncertain forever. Okay, now one special case of this spectrum non-polarization is exactly what we saw in the de Groot model, which is when the weights add up to 1. Because if the weights add up to 1, the row sum is equal to 1, which means the infinity norm of this matrix is equal to 1. The infinity norm is always, or any matrix norm, is an upper bound on the eigenvalues. So that means the eigenvalue is also 1. So that's a sufficient condition, right? No, not necessarily. So it's a sufficient condition for the norm is always an upper bound on the eigenvalue. If it's symmetric, it's exactly the eigenvalue for the 2 norm. But we're talking about the infinity norm here. Induced infinity norm, which is the row sum of this matrix. So this top eigenvalue could be 1 without the row sums being 1. How is that possible? Some of the row sums is less than 1. Some of the rows have sums greater than 1. Right? And then in the end, the spectral radius or the top eigenvalue can be 1. But we're saying a special case, which matches the de Groot model, is when the top eigenvalue is 1, which is like saying that the social learning rule is unanimous. What does that mean? That means if everybody reports the same belief, you also report the same belief, or that the vector of 1s is the fixed point of this map. When you have this situation, then you can also allow the weights to vary over time. Now, it's tricky the way that weights vary over time. There's an easy way to prove things, is to say that weights vary over time, but whenever they're positive, there's a uniform number epsilon where all the weights, when they're positive, are greater than that epsilon. That doesn't quite, even though that makes the proofs easy, that doesn't quite fit this model, because we'd like the model to represent that over time, I might dismiss someone's belief. So I want to let the weights to go to 0. But if I let the weights to go to 0, then the analysis becomes complicated. We can't use all the past. And so we had to handcraft some of the tools here. When the weights go to 0, then it's kind of, it should be intuitive that if the weights go to 0, that's kind of like disconnecting the network. And the network should not become disconnected too quickly. So the weights can't go to 0 very fast. Not only the weights can't go to 0 very fast, the ratio of certain weights also should not go to 0 very fast. Because if the ratio of weights go to 0 very fast, someone's influence becomes overt in this process. And no one person has all the information. The trick that makes the learning work is that the information, the correct information, is spread out across the network among all the population. Everyone has a piece of the truth, right? No one person has all the truth. So you need to gather information from everyone. And this is assuming there's no malicious misinformation. These are all cooperative agents. They all want to learn in this model. Okay? So you should not let influence of any one person get too large. And that's why the weights cannot go to 0. The ratio of weights cannot go to, they have to remain bounded from above and below for this to happen. Now, we didn't talk about the linear model. Where does the linear model come from if it doesn't come from our axioms? Well, the linear model comes from a variation on that IIA, the independence of irrelevant alternatives axiom. There we said when you condition the beliefs, you can commute with this operator. Here we're saying something stronger, the beliefs should be totally independent of other states. So if I care only about your belief on state 1, the functional form should only depend on your neighbor's belief on state 1 and nothing else. And if you change that axiom, then the only rule that pops out is a linear or an affine rule. So our result also gives a sort of a foundation to these type of models. Now, I know I'm running out of time. In the next few things, I want to say something about when does the Bayesian model actually, the rational model, satisfy this update. To make things simpler, I'm going to state a simpler sufficient condition. Basically, you don't want to have situations like this. If your network doesn't have situations like this, where there are multiple independent paths, then the Bayesian model does not satisfy some of the axioms that I stated. And interestingly, these are also the cases where our hardness result also comes from. Okay? So why is that? Well, if you have these multiple independent paths, then it becomes hard to remove this redundancy in the data. The trick about the Bayesian updating that our behavioral updates does not represent, and you see this also in the quintessential Bayesian case, which is Kalman filtering, which is when things are Gaussian and the models are linear, we know how to do the fully Bayesian scenario in the centralized case. Okay, so how does that work? You always compute innovation. So what is the innovation? It's the part of the information that is new, right? You extract the redundancy in the information before using that information. That's the trick with the Bayesian update. The updates that are myopic and they have this imperfect recall property might double count information because you're only listening to the last thing that people tell you. You're taking the last belief that they communicate to you as a representation of all that they know, right? Whereas some of that information might be something you already knew, and a Bayesian agent would remove that part of their belief. That's why a Bayesian agent, in principle, in certain settings, could put negative weights in someone's belief because it says, well, this I already knew, so I'm going to discount your information before I include it. And having networks like that makes this hard to do. So if you don't have situations like this, then in fact the Bayesian update also is log linear, except that it now doesn't suffer from this recall property. It includes the entire history. And turns out the coefficients here have a nice interpretation. Without going into too much detail, they come from enumerative combinatorics. They're a way of counting. It's the same thing that you do in inclusion-exclusion lemmas or in De Finetti's theorem, or if you want to take the unions and then you subtract the intersections. It's the formal way of avoiding the double counting. And you can do this well when your networks have certain structure that allows you to do this, avoiding this double counting easily. So there's a way to describe these coefficients recursively. In a way, these coefficients are some form of a discrete integration over a discrete structure. And if you have certain cycles, it messes up this integration process. That's, as I said, this is where the NP hard comes from. So these are the cases, some of the examples where the network can be and still satisfy these formalisms. Let me avoid this trip about, and then we show that the rate is exponentially fast. Let me say one thing here before I go.
The decay of 1 over t of the coefficient, this will not kill the rate?
The decay, if it's faster than 1 over t, it would. But up to 1 over t, it won't. Yeah. The thing is now, what if the rules are not log linear? So I don't want to parse all these detail. If the rules are not log linear, then this update would still work if it's a nonlinear function that is homogeneous of degree 1. What does homogeneous of degree 1 mean? It means that g of some alpha x is alpha to the 1 times g of x. Okay? So averaging and the log have these property, but there are a bunch of other functional forms that have this property. So if the function is homogeneous of degree 1, even if it's not averaging or the log, as long as its curvature is bounded in a certain way, and this is how we define it, the logarithmic curvature of this function has to be bounded, meaning that it can't be too far from the log linear structure. That's all you need to know about this. And that's a tight result, meaning that we can prove that if you're outside this regime, the learning doesn't work, which means you get either mislearning or non-learning. And this is the only site that it works. And then the rate depends on this time-varying notion of centrality, which we define as Kolmogorov centrality. And it also depends on how informative the observations are. It's a combination of these two things. So to make the learning fast, then you need to have most informed people also be most influential. Okay? There are certain cases when there is no ordering between who knows what, i.e. I know apples and you know oranges and we need both to disentangle the truth. In that case, you need the least informed to be the most influential. But if there is an ordering between who knows more, in a particular way, you can define formally what this really means. And that basically means that if I'm a single Bayesian agent, can I distinguish these states better than you or not? That's the ordering. If that ordering exists, then you want the most informed people to be most influential. So why doesn't we get learning? So there are a variety of mechanisms that we've now identified. One is the networks are not strongly connected. You have islands of people who don't talk to each other. The other is that the opinions are polarizing. So we saw that polarization actually hampers learning. A third is that maybe learning happens, but it's very slow because you've put the informed people in the fringes of the network. And it takes them a lot of time for the information to travel. So these are some of the mechanisms that we've sort of identified. We're trying to run some experiments. It's not easy to run experiments on these things. We've shown that group polarization is an obstruction, but surprisingly, learning is robust to the functional form of the update, and we've come up with tight characterizations of that. I wanted to say something about our institute, but I guess I'm running out of time, so I'll stop. Do you have maybe another 3 or 4 minutes? OK. So as you saw, my research has sort of somewhat shifted, still using decision theoretic tools. But now I ask a lot of social questions. So a bunch of colleagues and we decided that, OK, we need to create an infrastructure, a way for allowing this type of work to flourish. So we have a new institute at MIT, which is like a graduate interdisciplinary department, meaning with faculty and PhD program, and a micromasters program, that its focus is to combine systems theory, social sciences, and statistics and data science together. Partly, the third part is because MIT does not have a statistics department, so we're so we have about 16, 17 faculty slots across the institute. We hire these faculty with individual departments, so their tenure would sit in a department, but the slots are ours. And the idea is to sort of look at real-world problems, create either data-driven or mathematical models based on that, and then get insight from those. We have faculty across multiple domains, from social networks to infrastructure to healthcare, finance, environment, energy, autonomy. We've created a PhD. game theory, and so forth. And then we trained them in a social science. This could be microeconomics, macroeconomics, political science, sociology, and so forth, and also a domain. Basically, this is something in its second year. We're just doing the admissions for the third year. And if you need more information, I'd be happy to provide this. And if you could spread this to your students who might be interested, I'd appreciate it. So this is roughly the structure of our PhD. We have roughly 5 courses. You could call them analytics or information sciences that you have to take. You have to take 4 courses in a social science. You have to go in depth in something, and then 2 courses in a domain. And then we have a qualifying exam and research exam and so forth on this. So thank you for your attention.